This is joint work with Haim Kaplan, Or Zamir, and Uri Zwick. Two of the co-authors are sitting here. So I'll talk about the selection problem. So this is one of the classical problems besides sorting. It's one of the simplest things you can do on given n items, find the kth smallest of them. And unlike sorting, we can do this with a linear number of comparisons. So it's a bit hard to imagine today, but this was actually a major open problem back then. And this famous paper settled it. This, you probably know, it's this median of medians algorithm. There have been some improvements in the constants. It's still an interesting question, but I talk about a more general question, which we call generalized selection. So what if these n items, you know some partial order on them, you know some pairs, which is greater, which is smaller, and then find the kth smallest. So you have something like this, where the line means that this comparison, we know that one item is smaller than the other. So how many comparisons we need then to find the kth smallest? And in general, it is not known. So for the sorting, we have a pretty good idea about this question, but for selection, it's much less known. And the reason it's different for selection and sorting is that for selection, information theory doesn't give us very good lower bounds. So the easiest example is finding the minimum. So information theory just says that the minimum can be in n possible places, so you need at least log n comparisons. But we know that you actually need n minus 1. So this is...
What do you mean by the case smallest item in the partial order?
So the partial order is information that you already have, and you pay for the additional comparison.
Exactly. So the partial order is some comparisons which you already know for free, and then you have to make some extra comparisons to find the... So for example, in this example, the minimum can only be in one of these two places, so it's much easier than the... But how many comparisons should we make?
There is an underlying protocol.
Yes. So as I said, in general, it's difficult, but there are some interesting special cases. So one is that the partial order is a binary tree, so it's like a heap. We know that this is the smallest, and as we go down, everyone is larger than its parent, and then find the kth smallest. Another special case is you have a bunch of sorted lists. The same question. Another variant is you have a bunch of sorted matrices. So the matrices are sorted both by rows and columns, and then find the k. Slightly different flavor is you have an x plus y set, where you are given two sets x and y, and you have all the pairwise sums, and find the k the smallest. And it's important, x and y are not sorted. So these have been considered in the literature, and they have many. I won't go into the concrete applications. They come up in many problems, but the existing solutions are the best solutions are kind of complicated. So we give some simpler solutions. I'll go through them one by one. So the first question, as I said, we have a heap, and we want to find the kth smallest item. So suppose this is an example with some values. I don't know if it's visible. So how would you do it? The first algorithm which comes to mind, so find the kth smallest. Well, we know that the smallest is here in the root. So where can be the second smallest? Well, it's one of these two, right? So where can be the third? So first, which is the second smallest? Well, it's the smaller of these two. So it's this one. Now we have to expand down, and now the third is the smallest among these. And then this is the smallest, so we expand further. So as we go, we maintain a frontier in this heap, and we always have to pick out the smallest from this frontier. And then we expand the frontier to the children of that smallest. So this is this takes k log k comparisons, because how do you maintain this frontier? Well, you use a secondary heap, like a Fibonacci heap or something, and you pay log k for popping out these minima, so it's k log k overall. This is just the algorithm I mentioned. We insert the root into a secondary heap q, and then k times we extract the minimum and add the two children. Another pictorial view, this is our heap, and we have this frontier which is currently in a secondary heap. these we extracted already, and these we haven't seen yet, and we expand this frontier downwards. And just a remark that this achieves something stronger. This also sorts the k elements because we get them in order. So if we want to do something better than k log k, we should not sort the elements. Okay, so there is a non-trivial algorithm by Frederickson in '93 which achieves order k. And what he does is he starts with the trivial algorithm k log k, then he makes it much more complicated and achieves k log k. Then he sketches how you can nest that construction and get k log k. Then he gives a different algorithm which is k 3 to the log star k, he improves it to k to the 2 to the log star, and then finally he gets needless to say, this is extremely complicated. It's a very nice algorithm, but it's not something you want to go and implement the next day. And this is also tight. It's not hard to see that order of k is the best. How to see it? Well, where can the first k elements be? They are always in a subtree which contains the root. And there are Catalan numbers, possible subtrees, which is like roughly 4 to the k. So the logarithm of that is order k. Our result is matching running time, so order of k time algorithm, by essentially running the trivial algorithm, but instead of a secondary heap, we use a secondary soft heap. Okay, so what is a soft heap? It's so the soft heap is a very mysterious data structure which was introduced by Chazelle in 2000, and it was improved and simplified by Kaplan, Tarjan, and Zwick in 2013. If we compare soft heaps with something like Fibonacci heaps, we can see that they achieve the same cost on all operations, but they can do extract min instead of log n in log 1 over epsilon, where epsilon is a parameter. So it could be even constant. So this cannot possibly be true, because then we could sort with soft heap in better than n log n time, right? So there is a catch, and the catch is that the soft heap may increase some of the keys. So it doesn't keep your data in a reliable way, but when it increases some key, we say that it's corrupted. So the soft heap corrupts some of the keys. And we have this guarantee that at most epsilon n items in the heap are corrupted, where n is the total number of insertions so far. So this epsilon is a trade-off. We want to make it small, but then this cost becomes larger. So if we put epsilon to 1 over n, we get back the classical heaps. But if you think about this guarantee, it doesn't seem very strong. For example, it could be that every element that you extract from the heap is corrupted. So this seems a bit like a joke, like it wouldn't be very useful. But actually, it turns out to be very useful. For example, Chazelle uses it to get the current best minimum spanning tree algorithm. And another application, Petty and Ramachandran obtain actually an optimal minimum spanning tree algorithm, which the running time is not yet known. And more relevantly to us, Chazelle gives some applications to selection and approximate sorting. So let me sketch this, how you can use soft heaps for classical selection. So you have n items, you want to find, let's say, the median. You put these items into a soft heap. Remember, epsilon n can be corrupted. Now you extract half of the elements. And this half of the elements, these we extract, were the smallest at the time we extracted them, even by their corrupted increased key. So they surely were smaller than those half which remained in the heap, except maybe epsilon n if those were also corrupted. So these guys are smaller than n half minus epsilon n. And then we find the maximum among these extracted items, and the maximum has rank at least n over 2. So if we set epsilon to like 1 over 4, it means that we found a good splitting element, which is more than half and less than at least 1/4 of the elements. So then we can recurse on one side, and and we get median or whatever we want in. So this is very nice. how do soft heaps work? So I won't have time to give all the details. It's similar to classical binary heaps. So what happens? You extract the minimum. You get now the root is empty. So you want to propagate up some elements. So you take the child which is smaller and you move it up. Now you move this up. Now you move this up. So soft heap does the same. But in one node of the tree, it stores not just one key, but a bunch of keys. So a bunch of keys are grouped together and stored in one node. And this is where the corruption comes from, that if I store a lot of keys, then actually their representative will be just the largest of them. So all these will behave as if their key was this largest one. And also these groups are such that at the root they are very big groups, but as we go down, they are smaller and smaller exponentially. So, yeah, so each node contains a list, and so most of the corruption is near the top. And as we go down, it's like in the real world, sort of. So and far from the top, there is no corruption because each node has like one element, so it evens out. I won't go into the detail, but you get this epsilon and guarantee. So okay, back to the selection in heaps. So here is how we change the algorithm. We still go down from the root. We maintain this frontier, but we store it in a soft heap. And what we have above is not just those that we extracted already, but also those which got corrupted. So if something gets corrupted, we pretend that it was deleted and expand to its parents. So the algorithm changes, like you insert the root into a soft heap, and k times extract the minimum, and then you insert back into the soft heap the children of the extracted item, and also the children of the newly corrupted item. So the soft heap tells you which keys have been corrupted, and you expand those also. So there are two claims which show that that this gets the k selection. So in k iterations, we actually meet the k smallest items, and in total, we don't have to insert more than a linear. So then we end up with the order of k smallest elements, and then we can do a classical selection to find the actual kth among them. Yes, so I will only sketch these proofs. So as I said, we always have this barrier, which are the elements currently in the soft heap and not corrupt. And we have the property that what we extract is always the smallest on this barrier. And also, it's always larger than what we previously extracted from the barrier. So in k-1 iterations, we had to extract at least the first, the k smallest elements. So this is all. And for the other part that we didn't have to insert much more than k, we just use this bound using the epsilon. So if the number of insertions is I, the number of corrupted items is c, we know that I is less than 2k plus 2c, because when do we insert an element? When we extract something, which is k times, or when something is corrupted, which is c times. And also, the number of corrupted elements is, from the guarantee we have, is epsilon times I, plus maybe those k which we popped out, which may have been corrupt. So then we do some manipulation, and we find that for, let's say, epsilon 1/4, we get total running time order of k. So this is all for the algorithm. And now I'll move to the second example, which was a collection of sorted lists, or otherwise saying row sorted matrix. So this is now a totally new problem. We have a collection of m lists, here shown as rows, and they are sorted in increasing order. So we want to find the kth smallest among these. And again, Fredrickson and Johnson have an even older paper from 1982, where they give an m log k over m running time algorithm. And first observation is that we can get order m plus k just by viewing this as the selection in a heap. So you can think of these as paths, because these are sorted, and we can put in front of it like a binary tree of m nodes to make it like into a, and then we attach these paths. So we get actually a binary tree of m plus k. Sorry, we get a binary tree with m dummy nodes here. So we have to select the m plus k, and we can use our previous algorithm. But actually, we get also an algorithm which matches this m log k over m of Fredrickson and Johnson. And here we can strengthen a bit the existing result. We get an output-sensitive result where ki is how much of the solution falls into the ith row. So these k smallest elements may be distributed somehow among these rows. And if they are exactly equally distributed, then this is the same as the k over m. So then each row contains k over m. But if the distribution is very uneven, then this output-sensitive bound is stronger. So just to sketch the result, it's very simple again. We split each row into blocks of size b, and we take the largest in each block as a representative. This is, let's say, what the solution is in reality. We don't know this. And these are the full blocks which correspond to the solution. And we choose B in such a way that it's small enough that most of the solution falls into full blocks. So if the block size is very small, then we don't have much in these partial blocks, and most of it is in full blocks. And the opposite criteria is that we want this B to be large enough that not too many blocks hit the entire solution. So it's sort of two opposite criteria, and selecting something like k over 2m works. So what we do, we just find the smallest m representatives. We do that by our previous heap selection algorithm. These blocks are contained in the solution. They cover at least half of it, so we can just throw them away and recurse with the remaining, and we just reduced k to half. So in log k over m iterations, k is down to m, and we can use so we have log k over m iterations. Each iteration takes m time, so we get this running time. We can get a slightly stronger result where it's actually log ni, where ni is the length of the block. So if the blocks are, the rows are of different sizes, this is very easy. We just, the rows which are smaller than this block size b stay out of that round. And we just work with the rest of the rows. And we observe that these long rows contain most of the solution. So a row participates in only log n I iterations, so we get this total running time. To get the output sensitive result that I mentioned, we use another trick. We actually have exponentially increasing size blocks. So now the block sizes are like 1, 2, 4, like this. There are some small tricks, but I won't go to the details. Basically, we have to, if we knew this quantity, then it would be easy. But because we don't know this quantity, we guess for it with a doubling strategy, and then we get the claimed running time. I won't give more details, but it's not very complicated. And then the last example that I mentioned is the selection from x plus y set. For this, Fredrickson and Johnson gave a same running time m log k over m. So m is the larger of the two sets. So we can view it like this, that we have the two sets x and y, and every entry is a sum of a certain element from y and a certain element from x. if y would be sorted, then this would be a same problem as before, because then the rows would be sorted. So if we can afford n log n to sort y, then we spend this another m log k over m and we are done. But we don't want to sort y. Another observation is that if we would put all these elements into a heap, a four-way heap, we could get m plus n plus k, but we don't want linear dependence on k. So what do we do? Well, we pretend that y is sorted and we use a row sorted algorithm that I mentioned before. But y is not sorted. But observe that we actually don't need the entire y sorted. We just need these block representatives that I mentioned. And those we can get sort of on demand. So we do an on-demand sorting where we get those representatives by repeated median finding. And again, we use exponential size blocks. There are some nice tricks with powers of 2, which I don't get into, but it all works relatively simply. And here also we match the result of Fredrickson and Johnson. So these are all the results. We simplify these classical results significantly, and in one case we give stronger bounds. So some open questions which remain. Can we use similar techniques for the sorted matrices, where the matrices are sorted in both directions? This we didn't do. It's not clear if it's relevant to our techniques. There is another related problem, a geometric problem, for which there is a very complicated algorithm in the literature. It's called slope selection. You have a bunch of points and you want to select from the slopes of the lines. Are there any other applications? It seems like a very simple and powerful technique which could have more applications. And the famous problem, if I mention this x plus y selection, is sorting x plus y, which is a bit different flavor, because here we know the number of comparisons needed, but it's a question, can we algorithmically do it efficiently? It's a famous open question which you may know about. So this is all. Thanks for the attention.
Questions?
Yep.
Maybe I missed it, but for the one with the heap, there is a lower bound other than OK?
For which one?
For the one with the heap that you presented, the O of K, is there a lower bound?
So the lower bound is omega of k.
Omega.
So it's a tight result. So as I said, it's because the first k results can be in any binary tree which contains the root. And the number of binary trees is roughly 4 to the k. So the logarithm of that is order of k. Okay, other question?
Thank you.